Okay, so let us talk about increasing, decreasing, and kind of how we tell when a function is increasing or decreasing. Visually, it's super easy to tell if a function is increasing or decreasing. I should say, whenever you're talking about the behavioral function, unless someone has said otherwise, we are always assuming that we're talking about kind of reading the function from left to right. So if someone says the function is increasing, it means that from left to right, the y values get larger. If it's decreasing from left to right, the y values get smaller. So here are some classic examples, which I imagine your teachers have shown you. Let's look at kind of the easiest example, f of x equal to x squared. Let's maybe not use this pen anymore. And kind of call some of the black pens. So this function, we know what this looks like. It's a usual parabola, like that. Goes to the point 0, 0. And we don't even have to really do any sort of analysis here. We can literally look at it and say, okay, it's decreasing everywhere to the left of 0, it is increasing everywhere to the right of 0. So I would say it's decreasing. I'm going to let people in. I'll remind you guys, just so you know, for those of you that have to wait to be allowed in, you can sign in with SSO, which gives you a lot more functionality, but also I believe makes it, I think, I could be wrong, I believe it makes it so you don't have to wait for me to allow you in. I think it just lets you in. I could be wrong. Well, everyone's coming in. Okay, all right. So this function is decreasing on the interval from -infinity to 0, exclusive, and it's increasing on the interval from 0 to infinity. And what I should mention here is that the point 0, 0, it's neither increasing nor decreasing, right? 0, 0 is an extrema. So this point here, that point is called a relative minimum. You could also call it a local minimum. So relative or local, same idea. These two words just mean that, so relative to everything next to it, or locally, it is the smallest thing. It might not be the smallest thing on the whole graph, on the whole function. It is for this one, right? That is the smallest thing for the whole function. But when you say a relative minimum or a local minimum, you just mean, oh, it's smaller than the things next to it. Maybe not everything, but definitely the things next to it. All right, that point is not counted as, so I will tell you, your textbook is great, does it the right way. There are other textbooks out there that would say that it was decreasing from -infinity to 0 inclusive, which is not technically wrong, but is wrong. Right? You should, if you're talking about increasing, decreasing, you should not include the endpoints unless there was a good reason to. And there isn't here. So typically we define a function to be increasing on an open interval. There are some small exceptions to that, I think. So decreasing here, increasing here. And then the way you can find where a function is increasing or decreasing most of the time is by finding where the derivative is respectively positive or negative. So if you look at the derivative of this function, yeah, it's time for some new ink in these black pens. So if you look at the derivative of this function, f prime of x is equal to 2x. And typically the process that we're going to go through is we're going to find where the derivative is 0 or undefined, which is usually the critical values. But the reason we're going to find that is because if you find where something is 0 or undefined, those are the only places where the sign can change, right? If you have something that's either positive or negative, the only way to change from positive to negative is to either go through 0 or to go through undefined. You don't really go through it, but like to cross over where it's undefined. So if we set this equal to 0, you're going to get x equal to 0. The number line for f prime, 0, where the derivative is equal to 0, that's our only critical value. And then on either side of that, the sign is always going to be the same. So if you pick a number larger than 0, like 5, and plug it into the derivative is equal to 10. I don't really care that it's 10, I care that it's positive. On the other side, if you pick a number smaller than 0, like -3, plug it in here, the derivative is going to be negative. And I also like to draw this, so that I can think about, well, that means that the function itself is decreasing where the derivative is negative and increasing where the derivative is positive. I highly recommend making this sign chart for the derivative like this, and then drawing going down or going up for the function, because when you start graphing things, having this is going to actually really help you see the shape of the graph. So I'm going to do this like every time I'm trying to figure out where functions increasing or decreasing, because it's helpful. Let's look at some more examples. Yeah, more examples. Yeah, let's see if any of these. Yeah, you look like you might have something you still. All right, so let me do one thing. Looks like most everyone's here now, so let me real quick screenshot everybody's names. All right. So let's look at this function, which is not on my list, but that's all right. Let's look at f of x equal to x cubed minus 6x squared. And again, I want to know where it's increasing, decreasing. I also would like to know where the critical values are, meaning where the derivative is 0 or undefined. We know for this function that the derivative is never going to be undefined, because this is a polynomial. Polynomials are defined everywhere. They're continuous everywhere. They're differentiable everywhere. We might draw it, we might not. So let's look. I know that my derivative here is 3x squared minus 12x. And again, I'm trying to find where the derivative is positive to see where it's increasing, where the derivative is negative to see where it's decreasing. But to really answer that question, I'm looking for where is the derivative equal to 0. Because if I know where the derivative is 0, then I know where it's going to be positive or negative. So solving this, we're going to factor. You always want to factor. So you could do the wrong thing and add 12x and divide both sides by 3x. The problem with that, dividing by 3x, you get x equal to 4. It's not wrong that x equals 4. It's just not the whole story, right? There's definitely another solution to this equation, 0. So you never want to divide by x, really. Yeah, exactly. And so the point I'm trying to make here is, yes, to the person who asked me, can we factor out 3x? Yes, not only can we should always solve these equations by factoring if we can. Occasionally, there are small exceptions to that, but generally, if you're not sure what to do and you're trying to solve a derivative equal to 0, factor. Or as my friend used to say, when in doubt, factor out. So, that reminds me. The friend who used to say that, she works in the Bay Area, but she recently applied for a job working for, I don't remember the name, CADS at UC Davis, the Center for African Diaspora and something else. I'll have to follow up with her and see how that job application went. So anyway, 3x times x minus 4, that's how that factors. And we get two solutions. We get x equal to 0 and x equal to 4. So then throw those on the number line. Make sure that when you write them on the number line, you do write them in the correct order. Smaller numbers on the left, bigger numbers on the right. And then you're just going to check each interval. Now, one way you can do this is checking a point in each interval. Right? You can check like 6 and 2 and -1. But there's kind of a faster way, which I'll talk about here. So you still have to check one place. I usually check the rightmost place because I don't know, this is what I do. So check x equal to 6. Plug in 6. 3 times 6 is positive. 6 minus 4, is positive. And then positive times positive is positive. Oh, and I should point out, right, we're checking f prime, right? We're checking what the derivative's behavior is. It's positive or it's negative. So then one option would be to continue doing this, right? Check x equal to 2. 3 times 2 is positive. 2 minus 4 is negative. A positive times negative is negative. Or you could say, well, look, x equal to 4 came from this factor, x minus 4. And x minus 4 is raised to an odd power. And we know that when an intercept, not that it's an intercept of your graph, but like if you were thinking of this as your graph, we know that when you have an intercept, if an intercept has an odd power, you cross the x-axis. You change signs from positive to negative. 0 would be the same thing. 0 came from this factor, which is also to an odd power. When you hit an intercept with an odd power, you change signs. You cross the x-axis from negative to positive. Or you could pick points, right? You could say, okay, I'm going to plug in -1, -3 times a -5 is a negative times a negative, which is a positive. Do whatever is most comfortable for you. I find it to be a little bit faster to think about the multiplicity of the factor that the intercept or that the critical value came from. So that's what I usually do, but whatever is best for you is what you should do. So then I know that my function is increasing and then decreasing and then increasing. So I know that the function is increasing on the interval from -infinity to 0 union 4 to infinity. Again, right, we're not including those endpoints. And then it's decreasing on the interval from 0 to 4. A couple tips about writing your interval notation. You should just like with the number line, in interval notation, your smaller numbers go on the left, your bigger numbers go on the right. So this interval here, I'm doing the left number, -infinity, up to the right number, 0. And then this interval here, the left number 4 up to infinity. For this interval, the left number 0 up to the right number 4. So always left, right, never right, left. What else do I want to say about this? Not a lot. I will show you the graph. So definitely what we are working towards here, and working towards a couple things. One, being able to do optimization problems, and 2, being able to graph things. So I will tell you that this function, which you could factor out an x squared, and be left with x minus 6. So I was going to graph this. I know it's going to have an x-intercept at 0 and at 6. And then it's going to have this shape. Left of 0, it's going to be increasing. Right of 0 up to 4, it's going to be decreasing. And then 4 onward, it's going to be increasing. So knowing the sign of the derivative really helps us with the shape of the graph. It's up, it's down, it's up. I will also point out that we do have, at this point here, at 0, 0, we do have a relative maximum, meaning it is the biggest thing relative to what it's next to, also called a local maximum. Locally, it is the biggest thing in its neighborhood. It's not the biggest thing overall, right? There are definitely bigger values of the function over here. So this is a relative maximum. It is not an absolute maximum. Similarly, right here, at whatever that point is, we have a local minimum or a relative minimum. Locally, it is the smallest thing around. Not overall, right? Overall, there's definitely smaller things way over here. But in its neighborhood, that is the smallest thing. So that's what a local or a relative extreme is. It is the biggest or smallest thing in its neighborhood. Okay. Yeah, we should talk about that. So let's do more examples. Let's look at something like this. So let's look at f of x equal to x over x plus 1, which is definitely a question that somebody asked me. And I think they're asked to find increasing, decreasing. Oh, and yes, good question, Madison. Yeah, the critical values for sure. Yeah, I didn't actually answer that question. Yeah, so the critical values would be x equal to 0 and x equal to 4. And so just to be a little bit clearer with my language, Critical values are the values where, are the x values where the derivative is either 0 or undefined. There's a tiny extra little piece there, which the next example will kind of get into. The other thing I want to say is if you're talking about what the maximum or minimum value is, right? So if I said like, what's the relative maximum value? Well, it's 0, because when you plug in 0, you get out 0. What's the relative minimum value? Well, it's whatever the y value is here. So I guess what I'm trying to say is when you have a critical point, it occurs at the x coordinate with a value of the y coordinate. Well, what I'll say, so someone asked me a question about, do we need to calculate horizontal and vertical asymptotes for these types of functions in order to graph them? And the answer to this particular question is no, because it doesn't have them. Polynomials never have asymptotes. Never have vertical, never have horizontal asymptotes. But in general, the answer is yes. When you are graphing something, if there are asymptotes, you do need to graph them. It's just that a polynomial is never going to have any kind of asymptote. Rational functions definitely do. Yeah. In general, yes. In general, when you're graphing something, so I should say, if I am asking you to graph something, in general, I'm expecting you to find all the things. So we'll talk more about this as we go on. But when I say all the things, I mean y-intercept, x-intercept, vertical asymptote, horizontal asymptote. And then now that we're doing calculus, all the first derivative things, meaning all of the relative extrema. And after we talk about the next part, all of the second derivative things, which are the inflection points, and talking about where it's concave up and concave down. So those are the 6 things we usually look for when we're graphing: y-intercept, x-intercept, vertical asymptote, horizontal asymptote. First derivative stuff, meaning relative extrema and where it's increasing, decreasing. Second derivative stuff, meaning inflection points and where it's concave up, concave down. That's the list of things we look for. At least that's the list of things I think you should look for when you're graphing something. If your teacher has said something different, you should definitely do what your teacher is asking you to do. Let's look at finding where, again, let's do the same thing. We're going to find where it's increasing, decreasing, and we're going to find the critical values. So I really should show it the other way, because you have to kind of find the critical values to be able to find where it's increasing or decreasing, unless you happen to know what the graphing looks like exactly. Let's take the derivative. So we're going to use the quotient rule. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So this is going to equal x plus 1 minus x is just 1 over x plus 1 squared. And again, to find the critical values, we're looking for where this is either 0 or undefined. Okay, everybody tell me in the chat, where is this undefined? Undefined at x equal 2. Nobody has written the answer yet? Oh yeah, there we go. Okay, someone wrote yes. When the bottom equals 0, perfect. Yeah, exactly. X equals -1. Okay, now this is where we have an important clarification, but it's not that important. So here's what I want to say. -1 is not a critical value of this function. And the reason it is not a critical value of this function is because it's not in the domain of the function. So critical values are places where the derivative is 0 or undefined and where the original function is defined. So this is not a critical value because if you plug it back into the original function, it's undefined. However, it's still an important point. It's still a place where the, what's what I'm looking for? It's still a place where the sign of the derivative might change. So even though this is not technically a real critical value, if I was asking you to graph this function, it is definitely a point that would go on your number line for the first derivative. For sure, absolutely. It's also an important point because you know you have a vertical asymptote there, right? The function itself is dividing by 0 if you plug in -1 for x. That's definitely a vertical asymptote. So even if something is not technically a critical value because the function is not defined there, it should still end up on your list. of important things that go on the number line for the first derivative. So if I was making my first derivative sign chart, I would definitely be putting a -1 there, even though I know the sign's not going to change. So pick something larger than -1, like 0, plug it into the derivative. Well, look at this. This derivative is always positive if it's defined. If you plug in 0, 0 plus 1 is 1, 1 squared is positive. Oh, it's positive. And then pick something smaller than -1, like, well, or you could say the -1 came from this factor that has an even multiplicity, so the sign stays the same. Or you could pick something like -4. -4 plus 1 is negative, but the negative number squared is positive, so this whole thing is positive. So here's what that means. It means that the function itself is increasing and then increasing. All right, so this is where we have to be extra careful. What interval is this function increasing on? So let me ask you guys, I'm going to write 2 answers, and I want everybody to vote. So I'm going to ask everybody to type A or B in the chat. So answer A, it's increasing on the interval from -infinity to infinity. Answer B, it's increasing on the interval from -infinity to 0, union 0 to infinity. All right, I'm going to count down from 5, and then everyone's going to type A or B in the chat. All right, so is it this one, everything, or is it this one we're missing 0? So in, sorry, not 0. You guys like, it's neither of those, you foolish man. Sorry. Right, that's the place where it's supposed to be, yeah. Okay, so 5, 4, 3, 2, 1, your answer is yes, exactly. Good, you guys are on top of it. B, right? We can't say it's everything because the function's not defined at -1, right? It's increasing on the left, it's increasing on the right, but at -1 it's totally undefined. And to further emphasize that point, here's what the function actually looks like. Vertical asymptote at -1, horizontal asymptote at +1. We would have a y-intercept at 0. It looks like I wouldn't say that, Marshall. I wouldn't say it looks like a cubic graph. Yeah. In fact, the cubic graph is, well, that's my next example, actually. So this one looks kind of like this. It's increasing, right? As you go from left to right, it's getting bigger and bigger and bigger and bigger and bigger. It's undefined at -1. And then from left to right, it's getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. But it definitely wouldn't make sense to say it's anything that's happening at -1 because it's totally undefined. Yeah, you were way off. It's okay. Sometimes we're off. Anything else I want to say about this? Clearly this graph has no relative extrema, right? This graph has, so if someone asked you what are the critical values of this function, you would say there are no critical values. Even though -1 is an important point, it's not a critical value because there's a vertical asymptote there. You can't have a critical value where you have a vertical asymptote. Okay, so let us look at this next example, because this next example it's a reminder that we have to be careful. So let's look at the example f of x equal to x cubed, which hopefully we all do know what this graph looks like. We're going to graph it in a minute, but let's do it's usually good to kind of think about finding critical values and increasing, decreasing intervals without relying on the ability to graph the thing, because we're not always, at least I'm not always going to be capable of graphing every function, right? Some things are just, not that they're impossible to graph, they're just challenging to make an accurate graph. Whereas x cubed is something we're like, oh yeah, we know what the graph is. Well, let's find the critical values. So we're going to take our derivative, which is 3x squared. We're going to set it equal to 0. And the only solution here is x equal to 0. So my only critical value is x equal to 0. By the way, difference between a critical value and a critical point. The critical value is just the x value. The critical point is the x and y coordinate. So let's go ahead and make our little number line. So there's my critical value, it's 0. And then I'm looking at my derivative. And I can see that on either side, right, if I plug in 1 or -1, 3 times whatever I'm plugging in squared is always going to be positive. Positive here, positive here, which means, of course, my function is increasing, much like the previous example. Okay, but now here's the difference. This function, f of x, is increasing on what interval? This interval or this interval? Well, is it A or B? I see a little less agreement on this one. So it's a really interesting question. Is it A or B? And the answer is it's actually B. Let's talk about why. So the short answer to why it's B and not A, and the difference here is that basically, here's the way you can tell if you need to include the point or not. If it's increasing, basically if it's doing the same thing on either side of a critical value, and the function's defined at that critical value, you should include it. Which it is, right? F of 0 clearly defined, right? This is the polynomial defined. On the other hand, if it's increasing, or doing the same thing on either side of a critical value, and the function is not defined the critical value, you can't include it, right? Because the function doesn't exist at -1. It certainly can't be increasing at -1. But you might say, James, that doesn't make a whole lot of sense to me because I was always taught that to be increasing, the derivative has to be positive. That's not entirely true. It's usually what we check to see if a function is increasing. Like we're like, oh, is the derivative positive? Then yes, the function is increasing. But you can have one point between two intervals of the function of the derivative being positive where the function is still increasing even though the derivative is 0. Let me show you. So here's my not very good graph of x cubed. It does this, right? And we know that right there at the origin, the curve does flatten out, right? It has a horizontal tangent line. Okay, but if you look at this, entire function, if you pick any 2 points, the left point will be a smaller y value than the right point. And that is the actual definition of what it means to be increasing, right? If you pick any 2 points, x1 and x2, right? Maybe here's x1, maybe here's x2. To be increasing means that if x1 is smaller than x2, then the y value for x1 has to be smaller than the y value for x2, which it clearly is here. But the thing is, that's true for any point in the domain of this function, including x equal to 0, right? If you pick a number smaller than 0, a negative number cubed is negative, whereas 0 cubed is 0. If you pick a number bigger than 0, a positive number cubed is positive, and 0 cubed is 0. So if you pick something to the left of 0, it's going to have a y value that's smaller. If you pick something to the right of 0, it's going to have a y value that's bigger. So this function is increasing everywhere. You don't have to be super well versed in like kind of all the background here, but what you do need to know is that if a function is, if the derivative is positive on one side and positive on the other side of a critical value, or negative and negative, right? If it's doing the same thing on either side of a critical value, if the function is defined there, include it in your interval. If the function is undefined there, do not include it in your interval. That's the answer. That's the story. So kind of a little bit funky. I will point out we don't very often run into this issue. Usually, most of the time, if you're getting something that's increasing, or decreasing, often the function is just undefined at that point, but not always. So yeah. Sure, yeah. We'll come back and we'll see another example of this in a little bit. Let's look at some other things. Let's see, I know there were some other questions people had. Let me look at my notes real quick. Let me check off what I've done so I don't forget. That one. Still have that one. Okay, yeah. So someone asked me this one. This one shouldn't be too bad. So this one, in fact, negative 3x squared plus 7x. If I want to see where this function is increasing or decreasing, where the critical value is, I have some kind of prior knowledge, right? I know that's a parabola. I know it's opening downwards. So I know before I even get going here that it's going to be increasing from negative a to some x value of the vertex and decreasing from x value of the vertex to positive infinity, right? Because we know it's a parabola that opens downwards. We're still going to do the work. Also, by the way, in case you hadn't made this connection already, if my function was some general parabola, like ax squared plus bx plus c, and I wanted to find the critical values, I would take the derivative, which is 2ax plus b plus 0, set it equal to 0, solving for x, 2ax equals negative b, x equals negative b over 2a. Well, how about that? It's the x coordinate of the vertex. That always works. So in case you hadn't seen this before, I just want to point out to you, oh, this is kind of one of the reasons why we find the x coordinate of the vertex by setting x equal negative b over 2a, because you're really finding where the derivative is equal to 0. Kind of neat. How about that? Okay, well for this, so I mean, you could actually just say negative b over 2a here, but let's actually do the work. Let's take your derivative, which is going to be negative 6x plus 7, set it equals 0. Solving for x, if negative 6x equals negative 7, x is negative 7 over negative 6, which is my favorite number, 7, 6. Oh, yeah. So now we want to find where it's increasing, decreasing. We already know the answer. We already know if it's this downward opening parabola, it should be increasing on the left and decreasing on the right. Let's check anyway. Pick a number bigger than 7, 6. Like 10. You don't have to pick the smallest number that's bigger than, right? Like, you don't have to be like 2 is like the nicest thing that's bigger than 7, 6. Let's plug in 10, right? Just go big. 10 squared is 100, negative 300, plus 7 times 10 is 70, negative 300 plus 70, definitely negative. Pick something smaller. If I can't pick 0, I usually pick 0. So plug in 0. Oh, I made a mistake. It's okay that I made a mistake, but I made a mistake. I plugged in 10 to the function. That's not where I'm supposed to plug in 10. I'm supposed to plug in 10 to the derivative. I'm plugging 10 to the derivative, I get negative 6 times 10, which is negative 60, plus 7, which is still negative. So do be careful, right? You have to plug into the derivative. That's why I usually write that there to remind myself that I'm plugging into the derivative. Here's something smaller than 7, 6, like 0. So here's how I caught my mistake. I was about to plug in 0, and I was seeing that if I plugged in 0, I was going to get 0. But you shouldn't get 0 if the point isn't a critical value. Or it should have been a critical value. So I was like, oh, I'm plugging it into the wrong place. I should actually plug in 0 here. If I plug in 0 here, I get 0 plus 7, which is 7, which is positive. So my function is increasing, then decreasing. So I would say that the function is increasing on the interval from negative infinity to positive 7/6, parentheses. And I'd say it's decreasing on the interval from 7/6 to infinity. I would also say that I have a critical value at x equal to 7/6. I would also say that I have a relative maximum at x equal to 7/6 with a value of, I didn't find the value. To find the value, you have to plug 7/6 back into the original function. So I'm going to cheat and say with a value of f of 7/6. And I know it's a relative maximum because the function was increasing and then decreasing. So if you're going from left to right, if you go from increasing to decreasing, you have a relative maximum. In fact, that's the first derivative test, which I suppose it's a good time to talk about. So the first derivative test says, I guess it's probably said, let me double check. I believe it says 3 things really. Yeah, okay. So I'm going to write it kind of in the abbreviated way. So first derivative test. So here's what we got. If, let me try and use similar lettering here. Let's see, yeah, okay. So if C is a critical value of f of x, oh, that's interesting. Why would you say that? Sorry, I'm reading this thing. So let f be continuous on the interval a, b, in which c is the only critical number? I mean, it doesn't have to be the only critical number. Okay, anyway. So that seems silly, but whatever. So basically, you've got 3 options. If c is a critical value of f of x, then we have 3 possibilities. Possibility 1, you have a relative maximum at x equal to c if your sign chart does this kind of deal. If the derivative goes left to right, positive to negative. All right, so if your function is increasing, decreasing, you have a relative maximum. You have a relative minimum or a local, or you can say local. You have a local minimum or a relative minimum at x equal to c if from left to right, you go from decreasing to increasing, or your derivative goes from negative to positive. And then you have neither a min nor a max at x equal to c if you don't have one of these 2 things. So basically, if you have a function that is decreasing, decreasing, or a function that is increasing, increasing. So where it's decreasing, decreasing, or increasing, increasing. Right, like x cubed, right? X cubed, you didn't have a relative maximum or minimum at the critical value because the function was increasing and then increasing. The other thing I should point out here is the function needs to be continuous on the interval. And it does have to be defined at c. Right? So if you have a function that's like increasing, decreasing, but it's undefined at c, you don't have a relative maximum there. So definitely key point, f of x needs to be not only defined at c, it actually needs to be continuous at x equal to c. And continuity at a point does require it to be defined at that point. So that gets you defining this for free. Let's look at some more examples. Yeah. Oh yeah, we got loads of time. Loads of time. This is kind of my plan for the whole day, is just to do lots of examples of this. But if there's other things you guys want to see, or things that are a little bit like, if you want me to get to like the second derivative test or other stuff, let me know. I'm just going to kind of keep doing examples like this. Next time that makes. So someone just asked me this question. Could there be an instance in a relative extrema case where we have an x value that makes f prime of x equal to 0, but the x value isn't considered a critical number? Specify relative extrema because I'm asking the case where there's no interval. Let me think for a second. Usually, I want to say the answer to that question is no, and here's why. Typically, if the derivative is 0, so again, so let me kind of back up. So to be a critical value, here's what has to be true. We have to have that first, so x equal to c is a critical value if the following things are true. Thing one, f of c exists. Has to be defined at c. Thing two, the derivative at c is 0 or undefined. So now let me go back to the question here. Can we have a critical value where the derivative is 0? Or I could say, sorry, could we have an x value where the derivative is 0, but it's not a critical number? So let me ask you guys. So here's the question that's being asked. Is it possible for the derivative to be 0 and for it not to be a critical number? Well, so if the derivative is 0, you've satisfied this part. So the only way it wouldn't be a critical number would be for this to not be true. So you'd have to have that the derivative is 0 and f of c does not exist. And I will tell you that's actually impossible. Here's why. It's a good question. I like this question. So here's the thing about a derivative existing. So if f prime of c exists, which it certainly does if you're saying it's equal to 0, right? If something's equal to 0, it exists. So here's the thing though, if a function is differentiable at a point, then it had to be continuous. There's a theorem about this, but basically it says differentiability implies continuity, or as I like to say it, to be able to be differentiable, you had to be continuous in the first place. But if you're continuous at a point, one of the 3 criteria for being continuous at a point is you have to exist at the point. So if you have the derivative at c exists and is a real number, then you cannot have the f of c does not exist. It's impossible. Because being differentiable implies that it had to have been continuous, which means that it had to exist there. It's a good question. It's good to think about like what these things really mean. So really, really kind of important point. The biggest takeaway from all of this, what I just said here, is that if f prime of x exists, meaning if f is differentiable at x, then f of x is continuous. If the derivative exists at a particular value, then the function is continuous at that particular value. Let's look at a couple examples that kind of get more at that point. So here are some of my favorite functions that are continuous. I should say, really not my favorites, but here are some of the classic examples of functions that are continuous everywhere, but not differentiable everywhere. And I can think of 3 nice examples. Was that in this class? I'm trying to remember. I don't remember if it was this class or another class where someone, no, I think it was definitely this class, where someone asked me, where we were talking about the difference between a cusp and a corner. Was that this class? I'm pretty sure it was. Okay, I'm about to finally, I looked it up that day and then totally forgot to talk about it. I'm going to finally circle back around and mention what the difference between a cusp and a corner is. There is actually a real difference. And I'll try to make sure I say it correctly. So here are 3 functions that are all continuous everywhere, but not differentiable everywhere. Classic, absolute value of x. Looks like this. And it's clearly not differentiable at 0, right? There's a corner right there, not differentiable there. We know that the derivative is -1 if x is less than 0. The derivative is +1 if x is greater than 0. and then the left hand and the right hand derivatives don't match up, so it's not differentiable there. Okay. Another classic example of being continuous, right? But it is continuous everywhere, right? You can draw. I totally drew it without lifting my pen off the board, right? Definitely continuous. So differentiability implies continuity, right? If it's differentiable, then it had to have been continuous. Continuity does not necessarily imply differentiability, right? You can have a function that is continuous everywhere that is not differentiable everywhere. Here's another example of this. F of x equal to x to the 2/3 power, which I always call the bird function. Why do I call it the bird function? Because I'm a weirdo. Also because it kind of looks like a bird, a bird that an adult with very little drawing skills would draw, like these birds. I always think of like seagulls, right? Those are birds, right? Or a young person might draw a bird like that, or an adult who can't draw very well. Or going for a certain aesthetic. Definitely continuous. Definitely not differentiable at that cusp. How do you know it's not differentiable there? Well, look at the derivative, right? If I take the derivative of this function, I get 2/3 x to the negative 1/3, which if I rewrite it, it becomes a little more obvious. Right, it's 2/3 x to the 1/3, or cube root of x. Hopefully you guys can all agree with me that if I plug in 0 for x, I'm going to get division by 0. Divided by 0 is undefined. So at 0, the derivative is undefined. Okay. So, right, this is not differentiable at x equal to 0. Still continuous, right? Continuous, continuous, continuous. The difference between a corner and a cusp is that specifically a cusp is where, how do I say this right? So basically, the slopes of the tangent lines on the left side of the point where it's undefined, the derivative is undefined, and the slopes of the tangent lines on the right-hand side essentially are approaching the same undefined value. So basically, and I haven't drawn this super precisely. Let me draw it a little bit better just to kind of emphasize the point I want to make here. If you look at this graph, it's very pointy at the cusp, but the tangent lines are getting very, very, very steep. They're getting very, very close to being vertical. In fact, at that point there, the tangent line would be a vertical tangent line. Which, how do I say this the right way? Yeah, so basically you have a cusp when the left side and the right side are both approaching having a vertical tangent line, and is pointy there. Yeah, whereas a corner, right, definitely you're not getting like a vertical tangent line on either side. You're just getting different values of the derivative. So specifically for cusp, you're supposed to have kind of like approaching the same value on either side for your slope of your tangent line, even if it's undefined. It's kind of a lengthy explanation. I wouldn't worry too much about it. Lastly, here's another example of a function that is continuous everywhere, not differentiable everywhere. And kind of not differentiable everywhere in a similar sort of way as the previous one, although not exactly the same. So the derivative here, the derivative of x to the 1/3 is 1/3 x to the negative 2/3, which is 1/3 times x to the 2/3, or if you prefer, the cube root of x squared. And hopefully you guys will all agree with me again that if I plug in 0, I'm going to get division by 0, which means my derivative is undefined. So definitely not differentiable at 0, but we know what this function looks like. It's the cube root of x. Totally defined everywhere. Kind of looks like that. Right, there's supposed to be some odd symmetry here. Definitely I've drawn my right side a little bit bigger than my left side. Oh well. So the thing about this is that what you have here is a vertical tangent line that goes through the graph right there. So this function is not differentiable at 0. Definitely continuous at 0, not differentiable at 0. And the reason it's not differentiable at 0 is because the tangent line is vertical and the slope of a vertical line is undefined. So if you have functions with vertical tangents, their derivatives are undefined there because, not because like it's pointing necessarily, right? This function is totally smooth, right? There's no jagged edges, but still undefined derivative at 0, 0. Something you'll maybe hear people say is that is that differentiable functions are smooth. And that's usually enough. Usually smoothness is a sufficient condition for differentiability, but actually not always. So what I like to say about being smooth is a necessary, but not always sufficient condition for being differentiable. This function is smooth, it's still not differentiable everywhere because I happen to have a vertical tangent line. Okay, so again, let me really emphasize here. Continuous functions are not always differentiable everywhere. The differentiable functions are continuous wherever they are differentiable. Or, as we like to say, if you know a function is differentiable, then you automatically know it's continuous. Okay, let's look at some more examples. That one, not quite yet. So let's find, I believe, so someone asked me a question and I asked for clarification, but I didn't get it. So I'm going to go with my best guess. Someone asked about the critical values of this function, 8x plus 5 over x, as well as other things. I think this is the right function, as well as increasing, decreasing. So let's find the critical values. So we're going to take the derivative. It's going to be, if I'm finding the critical values of this, I'm probably going to rewrite it as 8x plus 5 times x to the negative first. So then I'm going to differentiate. The derivative is going to be 8 plus 5 times the derivative of x to the negative first is -1 times x to the negative second. I'm setting that equal to 0 / undefined. Okay, there is a place where this is undefined. It's where the original function was undefined at 0. And it's maybe easier to see this if I rewrite this as f prime of x is 8 minus 5 over x squared. That makes it a little easier to be like, oh yeah, of course it's undefined at 0. So undefined x equal to 0. Is 0 a critical value? Hell no. So I should really back up. It's not a critical value, but it's still what I like to call an important point. Or what I usually actually call it is I call this a pseudo-critical value. Meaning we're still going to look at it in all the ways we look at our critical values. It's going to go on our derivative sign chart. We're going to ask if it's increasing or decreasing on either side of it. But we're going to remind ourselves that it's not actually in the domain of the function. We're going to start off by saying, I know that I have a vertical asymptote at x equal to 0. And once you say that, you've kind of cut off the possibility for anything else. You can't have an intercept there. You can't have a critical value there. You can't have a max or a min, right? You did nothing other than the vertical asymptote. Well, let's see. There might be some other critical values. There's probably something that makes this equal to 0. So if I was going to try and solve this, factoring, I mean, you could factor here. Most of the time, factoring is the right way to go. Here, I probably wouldn't. And the reason I wouldn't is because there's only one x to deal with, right? There's only one instance of x. I actually think there's an x squared. But right, there's not like multiple x's being added together where you have to factor out. So if there's only one instance of your variable, usually it's okay to kind of just try and solve for it. So I'm going to have 8 equal to 5 over x squared. You could multiply both sides by x squared. You get 8x squared equal to 5. X squared is 5/8. X is plus or minus the square root of 5/8. Okay, So let's put all of these on our derivative sign chart number line. We got a 0. We got positive square root of 5/8. We got negative square root of 5/8. And we're trying to see what's happening here. Yeah, that's not going to be fun. So I'm plugging back into my derivative, and I want to plug. So one reason you might want to factor instead is because once you start manipulating your equation like this, you can't really plug in points here. Right? You can't like be like, I'm going to plug in 10 and be like, positive or negative. So I'm going to plug in 10 here. I plug in 10 for x, you get 5 over 100, 8 minus a small number is still positive. Okay, so now I need to pick a number between 0 and the square root of 5/8. Just imagine you're picking something super duper small, super duper close to 0, like 0.00001. You pick a number super duper small, the denominator is super duper small, which means the fraction is super duper big. So you've got 8 minus a very big number. That's going to be a very, very negative number. And the same thing is going to happen if I pick a small negative number, because a very, very small negative number squared is a very, very small positive number. And dividing by a very small number makes your fraction get very large. So again, you have 8 minus a very large number, which is going to be negative. Over here, pick a negative number like negative 1 billion, plug in negative 1 billion. 1 billion squared is really big. 5 divided by a really big number is really small. 8 minus a really small number is very much positive. So here's what we've got. Our function is increasing, decreasing, decreasing, decreasing. So I would say that I have, well, first of all, increasing, decreasing intervals. I would say it's increasing on the interval from negative infinity to negative square root of 5/8. Union square root of 5/8 to infinity. I would say it's decreasing on the interval from the negative square root of 5/8, comma, I can't include 0 because it's undefined to 0. So negative root 5/8 to 0, excuse me, union 0 to the square root of 5/8. Do I have a relative maximum? Do I have a relative maximum? I do, because there is a critical value, right? These 2 points are actual real critical values. 0 is not, right? It's undefined there. But I do have a critical value where the function was increasing then decreasing. So yes, I have a relative maximum at x equal to negative square root of 5/8. Do I have a relative minimum? Yes, I do. I have a relative minimum at x equal to the positive square root of 5/8 because the function was decreasing then increasing. Okay. How much time? Okay, yeah, I got enough time. There's 2 more examples I for sure want to get to. I'm trying to cycle through my pen. Yeah, okay. Yeah, let's see. What's this example? I know I've got one in my head that I need to do. Yeah, that one. Okay. The right one. Sorry, let me think for 1 second here. Sorry, those black spots here. I know this is. I know. I should actually be able to find it over here. 1 moment. There's just one. Oh yeah, that one. I've got 3 examples I want to do. I just want to find the one that I'm actually thinking of. Sure, you'll do just fine. Sorry. Sure, let's look at this one. Let's say our function f of x is, yeah, that should be fine. X over x minus 1 squared. And I want to find, so here are the things I want to find. Critical values, any possible relative extrema, and where it's increasing, decreasing. So critical values, extrema, increasing, decreasing. I mean, and really, these are all part of the same question. if I ask you to find the extrema, that encompasses the other two things. You have to find the critical values to know where you might have a relative max or a relative minimum, and then you have to know where it's increasing or decreasing to be able to tell if it's a relative max or a relative minimum, if you're using the first derivative test, which is always the test you should use for maxes and mins. Second derivative test for maxes and mins is a thing. You'll use it in 16C for real, but you don't really need it. It's kind of, it's just a little bit extra. So, derivative time. Derivative here is going to be the bottom, x minus 1 squared, times the derivative of the top, just 1, minus the top, times the derivative of the bottom. So the derivative of stuff squared is 2 times my stuff, times the derivative of my stuff, which is 1. Come on in, Marilyn. Okay. All divided by the denominator squared, so x minus 1 squared squared. Here's an important thing to know. If you're taking a derivative of a quotient and the denominator is already raised to a power, you are always going to be able to factor something with that x minus 1 or whatever is in the power here. You're going to be able to factor some of that out of the top every time, if it's to a power that's like 2 or 3 or 4 or whatever. Because you're going to have it occurring and then its derivative, but its derivative is also going to have the x minus 1 factor because you had the derivative of that thing to a power and the k power came down and solved for it. Moreover, once you've all done and simplified, the power of the thing in the denominator should end up being exactly 1 larger than it was when you take the derivative. So yes, I know it's not 1 larger right now, but after I factor out and cancel stuff, I'm going to end up with an x minus 1 cubed. And then if I take the second derivative, after I factor and cancel and did everything, I would end up with an x minus 1 to the 4th in the denominator. Because every time you take another derivative, the power on the denominator gets exactly 1 larger if you simplify. But we're not doing that. So let's just simplify this. So I'm going to factor out an x minus 1. Right? When you're trying to solve something equal to 0, you want to factor out. Factor out an x minus 1. You're left with an x minus 1. And here you're left with an x times 2. All over x minus 1 to the 4th. We can cancel this x minus 1 with one of these x minus 1s. And then the numerator simplifies as, let's see, x minus 1 minus 2x. X minus 2x is negative x. So you get negative x minus 1 over x minus 1 cubed. Be careful here. I've seen too many students try to cancel another x minus 1 here. Nothing else cancels. If you really want, you can factor out a negative 1 from the top and say it's negative 1 times x plus 1 over x minus 1 cubed. But we cannot cancel anything else here. So this is going to be 0 or undefined. I really should have said or undefined, right? What are my critical values? Or I should say, what are the values that make the derivative undefined, even if they're not critical values? Positive 1. What are the values that make the derivative 0? Negative 1. So my critical values, or the things I'm going to put on my sign chart, even if they're not actually critical values, are negative 1 and 1. Yes, I know 1 is not a real critical value, but it still makes a difference for the sign chart where the function's increasing or decreasing. So picking it. So let me back up one sec. This is also why it's good to factor fully, because then it's really easy to figure out whether the derivative is positive or negative. The fully factored form. So pick a number larger than 1, like 5. Plug it in. Negative 5 plus 1, so that's a negative on top. 5 minus 1 cubed is a positive on the bottom. Negative over a positive is negative. And then you could just say, since each of these things, 1 and negative 1, are both coming from factors that are raised to odd powers, the sign should change each time. It should be positive here and then negative here. You can also check with the value though, right? Plug in 0, negative 1 over negative 1 cubed is a negative over a negative, which is a positive. Plug in negative 4. Negative 4 plus 1 is negative 3 times negative 1 is positive 3 over a negative number cubed is also negative. So positive over negative is negative. So my function is decreasing increasing, decreasing. I definitely have a relative minimum. I guess I should say where it's increasing, decreasing, but I'll do it in a second. So I have a relative minimum at x equal to -1, because it's decreasing to the left, increasing to the right. And if I was not being careful, I would say there was a relative maximum of x equal to +1, because it's increasing, decreasing. But then I'd be like, I don't really have a relative maximum there because the function is undefined there, right? Undefined at 1. So we do not have a relative maximum. You can't have a relative maximum at a place where the function is not defined. We don't have a critical value there. And our maximums only occur at critical values. Our minimums only occur at critical values. This is just a pretend pseudo-critical value that I put on my chart because I wanted it. It does help me though with the increasing, decreasing, right? It's increasing on the interval from -1 to 1. It is decreasing on the interval from -infinity to -1, union 1 to infinity. In case you're curious, here we go. The graph of this, I'll just show you. The graph of this looks like this. You have a vertical asymptote of 1, horizontal asymptote at 0, intercept at 0. And here's the great thing. The sign chart helps me draw the graph. Here's right. And then if I look for my y value at -1, I plug in -1, I get -1 over -1 minus 1, which is -2 squared. So -1 over 4 is -1/4. So here's what I know. I know my function is decreasing, then increasing, then decreasing. So it's going to look like this. And I know it has this weird kind of behavior over here because I don't have any other x-intercepts. So it can't cross the x-axis. I have to have a horizontal asymptote there. You can cross the horizontal asymptote. We did right there. But you can only cross the x-axis when you have an x-intercept. So look, right, I definitely do not have a maximum at x equal to 1 because the function is not defined at x equal to 1. So I just want to help you avoid making the mistake of saying there's a maximum there. There isn't, function undefined there. Okay. Here is an example somebody asked me about. I have changed a number slightly just to make it a little bit different. And this one actually, well, yeah, this one I think is, this one's a little bit, I'm not sure about the answer for this one, so I'm trying to say with all the words in the world. So let's say our function f of x is the square root of 25 minus x squared. And let me look at one thing here. Come on, where's my email? Yeah. Sorry, one second. Oh, it's literally right there. Cool. Show me the thing. Yeah. So this is I don't know whose homework this is, but it's section 3.1, part 1, problem 4. I've just changed some of the numbers. So the first question is, at what values is the derivative 0 or undefined? So basically, they're just asking for the critical values. So where is f prime of x 0 or undefined? So let's find f prime of x. If I'm differentiating a square root of something, I really would prefer to write the function as the something raised to the 1/2 power. Now, I don't love the way this question is phrased because I feel like it's leaving a piece out. Because when you ask where, well, so I should say, let me show you the answer and then let me tell you what they're looking at. So let's find the derivative. The derivative is 1/2 times your stuff to the -1/2 times the derivative of your stuff, which is -2x. I think it's always a good idea to write negative powers in the denominator as positive powers. I can also cancel a 2 here and a 2 here. So I'm going to rewrite my derivative as, I'm going to have a -x in the numerator, and I'm going to have a 25 minus x squared to the positive 1/2 in the denominator. Or if you prefer, -x over the square root of 25 minus x squared. Okay. So the question is, where is this derivative 0 or undefined? Well, what makes it 0? Well, that's going to be x equal to 0. Okay, now let me ask you, what makes it undefined? Anybody have any guesses as to what makes it undefined? Well, the answers they are looking for, there's two of them. They are 5 and -5. Right? If you plug in x equal to 5, you get division by 0. Same thing if you plug in -5. Here's the thing I want to point out that they're overlooking. They should have said what values in the domain of the function, because technically 6, 7, 8, 9, 10, anything bigger than 5 also makes this undefined because you got the square root of a negative number. So they don't mean for you to look for that, but I just want you to be aware that when someone says where is the derivative 0 or undefined, what they mean is where in the domain of the original function. And the domain of this original function is -5 to 5 inclusive. That's what they mean. So again, right, a function has to be differentiable. Sorry, a function has to be continuous to be able to be differentiable. A function has to exist to be able to be continuous. So to be able to even think about the derivative, you have to have been in the domain of the original function. Okay, so these are the 3 points that answer the first part of that question with my changed up numbers here. The second part, where is this function increasing? Now, this is where I think it's kind of maybe weird. So let's draw our number line, but we've got a limited number line, right? Our domain is only -5 to 5. So we're kind of stuck. So I pick a number larger than 0, it's smaller than 5, like 1. My derivative is negative over positive, so it's going to be negative. If I pick a number like -1, my derivative is negative, so positive over still positive, so positive. So my function is increasing and decreasing. Okay, now here's what I think the answer should be for the interval where it's increasing. I believe the answer should be that it's increasing on the interval from bracket -5 to 0, parentheses, because the function is defined at -5. And I believe it's decreasing on the interval from parentheses 0 to 5 bracket. Because let me show you what the graph is. I mean, I think you guys probably know what the graph of this is, but let me show you anyway. And then we'll call it a day. I won't do my last example, which is fine. It wasn't that important. So y equal to the square root of 25 minus x squared is what sort of shape? Well, I know if I plug in 0, if I plug in 5 for x, I get 0 for y. If I plug in -5 for x, I get 0 for y. If I plug in 0 for x, I get square root of 25, which is 5 for y. Does anybody know what the shape is? Guys are like, if I just wait, we'll see. It's true, I will. Okay, it's true, I will. We only got a minute left, so I'll say it. So this shape is a semicircle, right? If you square both sides, you get y squared equal to 25 minus x squared. And then if you add x squared, you get x squared plus y squared equals 25, which is a full circle, center of the origin radius 5. But since y equals a square roots only give you positive outputs, so this is the top half where y is positive of the circle with radius 5. So here's what the function looks like. And it's clearly, in my opinion, increasing from -5 to 0, right? There's no reason you wouldn't include the -5. So it's increasing from -5 to 0, exclusive of 0, and it's decreasing from 0 to +5, exclusive of 0 again. But right, you should, unless I'm totally wrong, right? So if you're doing this problem and you're not sure, I personally would say it's increasing on this interval But if that doesn't work, then I would try this. I really don't think that's right, because there's no reason to not include the point -5. But there could be a reason that I'm not thinking of.